Hello everyone. If you're anything like me, cooking is very difficult. Creating something that's both palatable and non-toxic is a challenge, so you can imagine my excitement when I stumbled upon this lovely graph from a questionable source, detailing the safe temperatures and times to cook a chicken. There are many great options, such as 140 Fahrenheit for 27 minutes, 150 Fahrenheit for 3 minutes, or instantly at 165 Fahrenheit. Of course, these figures don't give you the full picture. There are a lot more potential options to explore. Imagine this. You've just had a long, challenging day spent falling asleep in classes and doom-scrolling social media. Now you have to make yourself something to eat. Notably, all the aforementioned chicken temperature recommendations are for internal temperature. Nothing conducts heat perfectly, and chicken doesn't even do it very well, meaning that even if our oven is heated to a perfectly consumption-safe 165 degrees Fahrenheit, our chicken will still take quite a while to be edible. This is a problem we can solve. In order to speed things up, we can simply cook for less time at higher temperatures. The premise of this video is very simple. We're going to figure out a theoretical chicken recipe that truly allows for near-instant cooking. Now we can get into my flawed methodology. I'm going to arbitrarily set our desired cooking time to 1 second. In order for this thought experiment to work at all, we're going to ignore the fact that real ovens take time to heat up and assume that setting our theoretical oven to a certain temperature will cause it to instantly reach said temperature. To define what counts as cooked, we're going to defer to the guidelines set by the United States Food Safety and Inspection Service. The FSIS states that establishments producing cooked poultry products must achieve at least a 7-log reduction of salmonella in the product. A 7-log reduction means that for every 10 million bacteria present initially, only one should survive after cooking, and this is achieved by reaching 74 degrees Celsius. Now we can do the math. The lumped capacitance method is what we'll use to calculate our temperature propagation, and it relies on one key simplification. We're modeling our chicken as spatially uniform, meaning that any one part of our chicken is assumed to always be the same temperature as all the other parts. This allows us to use the equation time is equal to negative density, volume, specific heat capacity over convective heat transfer coefficient times surface area, all multiplied by the natural log of our target temperature minus our oven temperature over the initial temperature minus the oven temperature. Now we can start plugging numbers in. Our target time, as previously stated, is 1 second. According to this dubious source, the density of chicken is around 1,037 kilograms per meter cubed. Specific heat should be around 3.22 kilojoules per kilogram Celsius, which converts to 3,220 joules per kilogram Celsius. The convective heat transfer coefficient of a given fluid depends on its properties and velocity. In this case, the fluid is air and its velocity is determined by the specific oven we use. Let's say it's 30 watts per meter squared Kelvin, which is pretty reasonable for a normal oven. Our initial temperature can be room temperature, generally considered to be around 25 degrees Celsius. Our target temperature was determined earlier and is the 74 degrees Celsius needed to kill enough salmonella to placate the FSIS. This leaves us with our oven temperature, surface area, and volume. Our oven temperature is what we're solving for, so we're obviously not going to find a value for that. Volume and surface area can be decided however we want. I already tried this calculation before with a 5 centimeter cube of chicken and got around a result of 4.5 million degrees Celsius. This is completely absurd. For context, the core of the sun is around 15 million degrees Celsius. In order to figure out why things went so wrong, let's recall that lumped capacitance is based on the assumption that heat propagates fast enough through an object for every part of the object to be the same temperature. The Biot number is a way to quantify this. It's solved for with the equation Biot number is equal to the convective heat transfer coefficient times the characteristic length divided by the thermal conductivity. Characteristic length is generally defined to be volume over surface area, while thermal conductivity for chicken is around 0.5 watts per meter Kelvin. Lumped capacitance is a valid model only if the Biot number is below 0.1. The original 5 centimeter cube of chicken has a Biot number of 50. Let's redo our calculation with a 2 millimeter cube. Now we have a Biot number of 0.02. As expected, we also get a far more reasonable answer, 1,867 degrees Celsius, which is around the melting point of copper. So now we have our instant chicken recipe. Cut your chicken into 2mm cubes, then place in the oven at 1867 degrees for 1 second. And practically, this is possible. There are forges and kilns that reach high enough temperatures for you to toss your chicken cubes in and pull them out a second later, but you might not like the result. Proteins such as those in our chicken consist of amino acids, and this paper on amino acid thermal decomposition cites temperatures of between 185 degrees Celsius and 280 degrees Celsius for decomposition. We're going far past 280 Celsius. Not for very long, mind you, but definitely long enough for some level of thermal decomposition. I don't know how to begin calculating what would happen, but I can definitely say that our end result would be a little charred. And with that, our chicken adventure is finally done. Please leave your grievances in the comments. I'd love to know how many mistakes I made through the whole process. Now, if you'll excuse me, I have a chicken to cook.